Okay, and this is weird. We're the only ones here. Everyone else kind of skipped out. And it's also weird. Where are we? You'll notice that it's not a whiteboard here. It's even better than a whiteboard. It's a chalkboard. So, as you probably know, Fordham University, as well as many other schools, have closed down over concerns about the spread of the coronavirus. So, our class lectures have to be moved online somehow, and since I already record all my lectures and post online, I figured I'd continue to do that. The difference is, basically, since you're not here to ask me a question, you would either ask me a question in the comment section, or you would send me an email if you're a student of mine through Jupiter Grades, and I will address your questions and make clarifications in the next video. So I already sent an email explaining all this, so I don't want to waste too much time. I just kind of want to jump into the material. So we are doing series, and last class, I left you off with some examples to do. So let's actually just jump into those. State whether the following converge absolutely, converge conditionally, or diverge. And you have 4 examples to do. So this goes from 1 to infinity of cosine squared n plus 1 over n squared plus 1. The next one was n goes from 1 to infinity of minus 1 to the n cosine n factorial over n to the n. The next one, minus 1 to the n over n plus 1 to the n. The next one, minus 1 to the n over ln of the square root of n plus 1. So, another thing that's going to have to be different, you're going to have to make up, work a little bit harder than you usually work, I think, if this is going to actually be beneficial to you. So, for example, you're not here for me to ask you questions and, poke at you. So, basically, what I'm going to do is every now and then I'm going to say, hey, pause the video and try this problem. And what you should do whenever I do that is you should pause the video and try the problem. Because just watching me do everything here, it's not going to be as beneficial for you as it could be if you tried it on your own. So whenever I tell you, pause the video, try the problem, really need to take my word on this, you need to pause the video, try the problem. Because you're never going to know what you really understand if you just let me do all the work. That would also help you if you tried something and you didn't get the answer that I got, or you just didn't see where my answer comes from. That's going to be important. You're going to know to ask a question about that for me to address in the next video. So make sure you actually try these. So these you should have tried from pretty much the same day as last class, so a couple days ago. So if you haven't done these, pause the video, try the problems. Actually try them before I go into them. It's going to be very important. I can't stress to you how important it is. I don't want to spend a lot of time talking about how important it is, but it is super important. Okay, that being said, so you can pause the video for a long time. You can try all 4 of them, which you probably should have already, but if you haven't, you can do that. Or you can we can go through them one by one, but you pause the video before I do each one, and so you can know, would I have gotten the problem had I actually did it? If I did it myself? Okay, another thing that you'd want to notice with these guys, I'm still kind of trying to get used to. I already recorded a lecture, as you can see, I have lots of chalk on me, but I'm not used to being by myself and talking about math like this and talking to a camera. It's very weird, and I'm still kind of finding my positioning, and it's kind of weird. I have to stand more in the middle of the board now, otherwise it's kind of weird with me talking off screen. Anyway, let's not make this more awkward than it has to be. Okay, so pause it, try them, and one other thing that you need to know for this kind of situation, which I did mention in class, but I'll mention it again, is that whenever you are asked whether something converges absolutely, converges conditionally, or diverge, basically what you're going to do, well, first, always what you want to do first is test for divergence. That's always how every series problem is going to start. You're going to try a test for divergence first. But then what you're going to want to do is you're going to check for conditional, check for absolute convergence first. Now, if it converges absolutely, if yes, then you conclude that it converges absolutely, and you stop. If no, go to step 2. Step 2 would be to check conditional convergence. And if yes, you would conclude that it converges conditionally. And then you would stop. If no, then you conclude diverges. Okay? So when it comes to these problem types, you definitely want to check absolute convergence first, provided that the test for divergence actually doesn't give you anything useful. So remember, the test for divergence was the one that said, if you take the limit of the series part, usually when it's an alternating series you can ignore this part, but if you take the limit of this part and you don't get 0, the series is going to diverge. So that is going to tell you that you can just jump straight to conclude that it diverges. If the limit is 0, though, you cannot conclude that it converges. You have to try something else. Now, whenever I ask you about converges absolutely, converges conditionally, or diverges, you always want to check absolute convergence first. Because if you get conditional convergence but you didn't check absolute convergence, you're going to have to check absolute convergence. Because something can converge conditionally but does not converge absolutely. If something converges absolutely, it also converges conditionally. So getting this one, you get that one for free. But if you have this one, you don't necessarily have that one. So it always makes sense that if you don't know it diverges right off the bat, check absolute convergence first, then move on to conditional convergence. So if it converges absolutely, you're done. You stop the problem. Say, hey, it converges absolutely. If it doesn't, then you check conditional convergence. And remember what absolute convergence means. It means the series converges when you put absolute values around all the terms. So in step 1, you're going to put absolute values around all the terms, see if it converges. If not, remove the absolute values and try again with some other series test. Yes. And last time we also spoke about a strategy for approaching series. Just like how we have a strategy for approaching integrals, we also have a strategy for approaching series. Hopefully you should review that before doing this. And keeping this in mind, I want you to pause the video and try these problems. At least try the very first one. Once you've tried it, then you can start the video again and see, does your solution agree with mine? Or maybe, which is possible, you came up with a completely different solution. The answer does agree, but you got to it a different way. If you're not sure that you're right, that would also be something that you'd want to ask me about. Hey, Jhevon, I tried it this way. I want to know, would you have given me credit if I did it this way? And I can also talk about that. So that being said, let's just jump into the first problem. been a long day. I'm actually getting a slight headache right now, but let's get this bread, huh? Okay, so that's the problem. Cosine squared n plus 1 over n squared plus 1. All right, so first thing I would do, I'm not going to write it out because this one's probably a little bit easy to see. The limit of that does go to 0, right? So your cosine squared, right there. So your cosine squared, the biggest that could be is 1, so the largest the top can be is 2, and the denominator is an n squared plus 1, so that's going to go off to infinity. So you have a fraction where the numerator, the biggest it could be is 2, and the denominator is going off to infinity, so this limit actually approaches, the limit of this guy's n approaching infinity actually approaches 0. If you want to do that technically, you'd use the squeeze theorem, but you don't have to get too technical here because limit is 0 isn't going to tell you anything, so you don't want to waste too much time writing it out. So now that we know that the test for divergence isn't going to help us, now we're going to jump into the process. So 1, check absolute convergence. What does it mean to check absolute convergence? It means you're going to consider the series with absolute values around it. Now, the moment I throw absolute values around here, you should be thinking of certain things. Certain things should be coming to mind. And quite frankly, whenever there's a trig function, even if I didn't ask you about absolute convergence, putting absolute values is going to be useful because we have bounds for a lot of trig functions once we put them in absolute values. So cosine squared we know is bounded above by 1 in absolute value, which means that this series here is actually bounded above by 2 over n squared plus 1, right? Because the cosine squared, the biggest that can be is 1 plus 1, so this, the largest it can be is 1 plus 1, which is 2. Now, this is a new series, and in fact I can even clean this up a little bit more. This is going to be less than or equal to the series of 2 over n squared. Because here the denominator is smaller, so the fraction is bigger. Now what's nice about this guy is if I were to factor out a 2, that is a kind of series I know about. That is a p-series. So this here is a convergent p-series. P equals 2. Now, because we have absolute values around all the terms here, this is of course greater than or equal to 0. And so what you'll notice is we're in a situation for the comparison theorem here. So this series is that series with absolute values around all the terms. It's definitely larger than 0 because it's a bunch of absolute values. And then I realize that it is less than some other series that I know converges. The comparison test for a series tell us the bigger one converging in this situation implies that the smaller one converges. So what we can say then is this means the original series converges, and not only does the original series converge, it converges absolutely. How do I know it converges absolutely? Because the series with absolute values around it converges. How do I know that the series with absolute values around it converges? Well, by the comparison test. Okay. And that is the solution to the first problem. I think that's a pretty typical way to actually approach this problem. So I think most students who would have gotten this correct would have gotten it correct by doing it that way. You might have another way, and if you're not sure if that's that way could work, you can actually try that. But this is a pretty nice way to do it. You want to check absolute convergence, so throw absolute values around it. This allows me to bound the cosine above by 1, which means that the entire thing is bounded above by this, which is bounded above by that. Now this is a convergent p-series, which means that this guy converges by comparison. But if this guy converges, it means that guy converges absolutely. So my original series converges absolutely. How do I know? Well, I did a comparison with this to say that that converges. Now, if anything that I just said confused you, you're going to find the point of the sentence where you got confused, and you're going to look that thing up. So if you're like, I don't see how you apply the comparison test here. Well, look up the comparison test. If you don't know, how can I conclude that it converges absolutely? Look up what it means to converge absolutely. Make sure you fully understand, and if you don't, ask me a question. That's what I'm here for. Ask me a question. Put it down in the comment section, or shoot me an email through Jupyter Grades. Yeah, so comparison theorem tells me that because this is convergent, because I know it's a p-series, that is convergent. This is the original guy with absolute values, which means if this guy converges, that guy converges absolutely. So by applying the comparison test on this guy, I can talk about that guy converging. Absolutely. Okay, that's the solution to the first problem. It's actually an absolutely convergent series. Let's move on to problem part B. Problem B. Okay, so if you haven't tried this one, pause the video, try it. Try it. Did you try it? Did you pause it? Pause it right now. Try it. Did you try it? Did you try it? Okay, let's actually do it now. So, how would we know, does this converge? Absolutely, conditionally, or diverges? Well, the first thing I'm going to do is check the test for divergence. Note, if I look at the limit of cosine of this you should realize is basically, I don't need the limit, that's going to be cosine of 0. Why is that cosine of 0? Okay. Remember, we have a relationship which I've mentioned several times in this class, and it was mentioned. You're probably beaten to death with it in Calculus 1 as well. At least I beat my students to death with it. Logarithms are always much smaller than polynomials, which are smaller than exponentials, which are smaller than factorials, which are smaller than variable exponentials. Okay, so as n is going off to infinity, these guys have that relationship where guys on the right are much larger than guys on the left as your n is going off to infinity. So what you notice here is the denominator is an n to the n. It's much larger than the numerator, which is a factorial. So this here, this part here approaches 0 because you have pretty much a bottom heavy fraction as you're going off to infinity. And of course, now cosine of 0 is, that's right, it's 1. Now, what's so special about 1 in this case? Well, it's not 0 is what's special about it, which means the series diverges. How do we know it diverges? By the test for divergence. Using this to help me out, I know that that guy actually diverges. Test for divergence. So, of course, to do that, you have to know how to deal with limits. So yeah, so that was the answer to that one. So if you thought that that converged or you got something else going on, you probably want to look into a couple of things here. Probably check how good you are at limits, how good you are with trig functions, because you need to, yeah, whatever. Anything confused you about that, just ask me questions and I will deal with it next time. But let's keep going. Right? So that's part B, divergence, test for divergence. Let's get the third column, part C. Goes from 1 to infinity, minus 1 to the n over n plus 1, n. Now, if you haven't tried it, pause the video, try it. Pause it right now. Did you try it? Okay. All right, so, again, I would look at the test for divergence here. What's going to happen here? So, let's look at this limit. Now, at face value, look at what's happening inside the parentheses. It is approaching 1. You should be aware of that. The n is approaching infinity, so this is 1 to the infinity. It's an indeterminate form. Now, I'm extremely suspicious that that is going to give me a 0. It could give me a 0, but I'm very suspicious that it's going to give me a 0. So I'm thinking the test for divergence is going to actually work out nicely here. It's going to work out in our favor, because chances are that's not going to be 0, but it's an indeterminate form. We don't know. So how do we deal with that indeterminate form? Well, the convenient indeterminate forms, remember, are 0 over 0 or infinity over infinity. We know that from L'Hopital's rule. Here, 1 to the infinity. How do we deal with that? Well, it has a power. Bring the power down. How do you do that? With a logarithm. So what we would do... Oh, I'm actually going to show you a nicer way to do this one. A shortcut. And then we'll do it the longer way. Here's something that you could notice. This is actually that. And at this point you're like, yeah, so... Right, so I just took the reciprocal of the thing and then put 1 over it. Why did I do that? Well, in the bottom, I can just divide by n. That's 1 plus 1 over n. Do you see it yet? Now do you see it? That's right, that's 1, that's, as n goes to infinity, this guy actually approaches e. The limit is 1 over e, which in particular is not 0. So again, the series diverges. Now, you might not have seen it that way, even if you got to the right answer. It's worth mentioning, in my experience, few students will actually see this, but just so you know, this limit is something that you kind of should always be looking out for, and this expression becoming that expression is actually pretty common, believe it or not. If you're a Cal student who's practiced a bunch of problems, at some point you're going to see manipulations like this happen all the time, and you'll actually be able to see something like this. But the typical Cal 2 student with very little experience in working with limits or these kind of things probably wouldn't see that. Don't feel too bad if you didn't see this, but it was one thing that you could have done. Let's do it a more traditional way. So maybe you got to the limit by this way. So you could either notice the pattern that it's just a 1 over e limit, or you can go with what I was kind of setting up before. This is approaching 1 to the infinity, so it's an indeterminate form. I need to rewrite it into a more convenient indeterminate form. what I could do here is just introduce a logarithm by first introducing an exponential and putting the logarithm there. This allows me to bring the n down. And I know that limits pass through continuous functions, so this is just the limit of that. Now what I can do is rewrite this in a convenient way. Move the n from in front to the denominator and take its reciprocal. Now why would I do that? Notice what this approaches here. This would approach, as n approaches infinity, n over n plus 1 would approach 1, so the top approaches ln of 1, which is 0. And as n approaches infinity, 1 over n approaches 0. It's a 0 over 0 limit, which means I can apply L'Hopital. So I'm going to find the derivative of the top and the bottom. Now it's worth mentioning, just to make my life a little bit easier, I'm going to think of this as using the log rules ln of n minus ln of n plus 1. So that in applying L'Hopital's rule, derivative of that is 1 over n, derivative of that is 1 over n plus 1. Derivative of the bottom is minus 1 over n squared. So now I want to know what that is going to approach. And probably the best thing to do here is to actually simplify this. Let's simplify before moving on. So this guy here is going to be, if I add the fractions in the top, that's actually going to be 1 over n squared plus n. So equals e to the limit of 1 over n squared plus n over minus 1 over n squared, which means I can keep change flip. This is minus n squared. Okay. So, however, you can combine those fractions, combine whichever way you want. But I combine it, I get that. Notice that this now is minus n squared over n squared plus n. So this is actually going to give you e to the minus 1, which is what we got last time. So that's another way. That's probably the more traditional way to do it if you don't have a lot of experience with the e limit. Although you should have a lot of experience with the e limit. So that, in fact, this is not 0, which means series diverges. Yeah, so that's the second one. Well, the third one. Jeez. It's late, I have a headache. Cut me some slack, people. So the third one diverges by the test for divergence. What about the fourth one? Haven't tried it? Pause the video, try it. Did you pause the video? Did you? Okay. Let's actually try it. Clearly here, I mean, ignoring the minus 1 to the end, so just think of it as 1 over ln of blah, then clearly that's going to go off to 0. So the test for divergence is definitely not going to help us here. The limit of that clearly goes to 0. So I'm going to check absolute convergence. What would that look like in this case? Well, that would just be 1 over ln of that guy. Now, here's something that you can remember. We have a log rule. Ln of anything to a power is, you can bring that power down in front of the ln. Right? This works for logs in general, but it's true here, for example. So, in particular, if I had ln of the square root of something, that's just ln of the half power, which I'm allowed to bring the half down in front. So this is actually just a series of 1 over 1/2 ln of n plus 1. That's actually exactly the same thing, which, of course, with the half in the denominator, I can flip it and multiply. So this looks like that. So that's the series that I'm looking at, right? That's the series with absolute values around it. So if that guy converges, then the series will converge absolutely. So now the question is, does that guy converge? So let's look at this guy. The series n goes from 1 to infinity of 2 over ln of n plus 1. What are our options here? So we have a bunch of strategies to go through, and hopefully you have those strategies written down in one place and you have them beside you while you're working on these, as I kind of explained that you should be doing. You're going to be thinking about a lot of things here. One, can you break it up and do a telescoping thing? No. Is it geometric? No. Is it a p-series? No. Integral test? No. Basically now, what you're going to want to try to do is maybe a comparison. That's probably one of the next things you're going to think about. So you might want to know what to compare it to. Now there should be some that should be somewhat obvious that you might want to compare it to. And probably what you're thinking, I don't know, would be, it's what I'm thinking, so maybe it's what you're thinking. Without the ln, because the ln kind of makes that really annoying, doesn't it? If it were just that, that would actually be no problem. So now you want to think about, well, what would happen if I remove the ln? Well, we kind of know what would happen, don't we? By a relationship that we had earlier, logarithms are smaller than polynomials, smaller than exponentials, smaller than factorials, smaller than the variable exponentials. So, for me to actually go from a situation like this to a situation like this, this denominator is going to be larger than that denominator. If I get a larger denominator, I get a smaller fraction. So this guy is smaller than or equal to that guy. Do you see what to do now? If you haven't finished the problem, maybe try to pause right now and actually try to solve the problem. Okay, you had your chance. So this guy here, you will know obviously is larger than or equal to 0. And so we can actually use the comparison theorem here, because that guy should be clear to you that that actually diverges. This guy diverges since he is harmonic. Now, I know technically the harmonic series doesn't have an n plus 1 in the denominator, but a couple ways you can see that this is actually pretty much exactly like a harmonic series. if you start this from n equals 1, what is that going to look like? Well, it's going to look like 2 over 2 plus 2 over 3 plus 2 over 4 plus 2 over 5 plus da da da. Basically, what you realize now is that this is kind of like just 2 times a half plus a third plus a fourth plus a fifth plus da da da, which is now just 2 times the series n goes from 2 to infinity of 1 over n. This series is actually exactly the same as this series. It's just actually double this series. This series now is the harmonic series, except we don't include the first term. So it's like you take the harmonic series and you subtract the first term. It's still going to be infinite, right? The harmonic series diverges to infinity. If you're not comfortable with that, what you could also do is set up another comparison. Compare this to 1 over n. The limit comparison test would probably be the nicer one to do there. Yeah, the limit comparison, because 1 over n is actually going to be smaller than that guy, larger than that guy, which is useless. So if you don't see that, you could just do the limit comparison with this guy compared to the series of 2 over n, and you would get that that guy would diverge. But it should also kind of be clear, it's just a guy over a linear polynomial. It's harmonic. It would have all the same behaviors as the harmonic. It's just probably like a shift or something like that. However, since that guy diverges, and he's smaller than this guy diverges by comparison. What does that mean? Does our series diverge? No. So this basically means we don't have absolute convergence. The series could still converge conditionally. So, took a long time, but technically, in theory, all this should run through your head in fairly quick fashion. I mean, it's taken a long time because I'm explaining what I'm thinking so that you get it. But you should actually be able to get through this relatively quickly. So, put absolute values around it. You're going to notice that this equals that. You're going to notice that, hey, it'll be nice if the ln wasn't there, so I'm going to compare it to that. Because I know polynomials are larger than logarithms, that guy's a smaller fraction. He's also harmonic, so he diverges, which forces this guy to diverge, which means this guy with absolute values around him diverges. So now, go on to the second situation. You're going to check conditional convergence. Which means you're looking at the original series now. Now, looking at the original series, you are going to notice that that is, hopefully you notice, it's an alternating series. It has a minus 1 to the n. This part here is always going to be positive, and, well, I mean, after 1 it's going to be positive. It's not quite positive at 1. But after 1, no, it is going to be obviously positive. What am I talking about? So that's going to be at least ln of radical 2, which is going to be positive. So here's what we notice. an equals 1 over ln of n plus 1 is greater than 0 for n greater than or equal to 1. Also, notice that an is decreasing. That should be clear. The numerator is a constant, the denominator is an ln, which is growing. And look at the limit of an. Well, it's 0. So that tells us the series converges by the alternating series test. But how does it converge? Remember, when we put absolute values around it, it didn't converge. So it converges conditionally. And we mentioned last time that the absolute values, the alternating series test does tell us about conditional convergence. And that is the answer to the fourth one. Took a lot of time. I'm not sure starting another topic would be wise at this point. We're pretty much out of time. We have like 5 or so minutes, if I actually track the time correctly. We have 5 or so minutes left, but it's not enough to really get into what I want to do next. So we'll actually stop there. So we pretty much just did the examples that you should have worked on last time, but there's really a lot to unpack here. I've just been rambling on, but I do think it wouldn't be out of the ordinary for some students to have a lot of problems with what I just did. So make sure you understand what I just did. If you don't understand, again, drop your questions down in the comment section or send me a message at through Jupiter Grades, and I will address them at the beginning of the next lecture and then move on to the next thing I wanted to talk about. But I think at this point, that's enough.